All right, let's talk about one of the biggest headaches in engineering and physics, differential equations. But here's the thing, we're not going to do it by just grinding through pages of algebra. Nope. We're going to learn how to solve them way faster and way smarter by actually seeing the patterns hidden inside.
I mean, if you're in STEM, you know exactly what I'm talking about, right? That feeling of staring at a problem and it's just page after page of derivations. You're trying to solve an equation that feels almost identical to the one you just finished an hour ago. It's a total grind. So tedious, so time-consuming.
Okay, but what if I told you that for a ton of the most common problems, you don't have to start from scratch every single time? What if you could literally just look at the equation and instantly know what the answer is going to look like? That's exactly what we're diving into today.
Now, hold on. This isn't some magic trick or a cheat code that lets you skip the learning. It's actually the complete opposite. This is all about getting to a much deeper level of understanding, a place where you stop seeing just numbers and symbols and you start seeing the story the math is telling.
And that's the key right there. Every single differential equation you run into that describes the real world is telling you about a physical system. You know, how a cup of coffee cools down, how a spring vibrates, how a circuit behaves. And recognizing the pattern in that equation, well, that's like recognizing the plot of the story before you've even read the whole book.
So how do we actually do this? Well, here's a simple framework. First step, look. Just look at the equation structure. Does it have that classic look of exponential decay, or maybe a harmonic oscillator? Second step, match. Once you've spotted the form, you match it to a solution pattern you already know. Third, check the input. Is it being pushed by something simple, like a step function or a sine wave? Because those have standard answers. And finally, the best part, step 4, recall. You just pull that solution template right out of your memory instead of grinding through the derivation all over again.
Okay, theory is great, but let's make this real. Let's look at our first pattern. This one's a classic first-order system, and I mean, you see this thing everywhere. Thermodynamics, RC circuits, population models, even radioactive decay, it's all the same story. So on the one hand, you've got this super simple, real-world thing, a hot cup of coffee just sitting on a table cooling down. We've all seen it. And on the other hand, you've got the math that describes it perfectly, Newton's law of cooling. All it's saying is that how fast the coffee cools, the rate of change of its temperature, depends on how different its temperature is from the room around it. Makes sense, right? And bam! This is where the magic happens. This is the power of pattern recognition in action. The second you see that equation form, your brain shouldn't even think about separating variables or integrating. Nope, you should immediately see the solution pattern. You just know it's going to be an exponential decay, settling down to that surrounding temperature. You saw the plot, and you skipped right to the final chapter. All right, that was a good warm-up. Let's level up. We're going to look at our second pattern now, and this one's a bit more complex, a second-order system. And trust me, this pattern is the absolute backbone of like all of mechanical and electrical engineering. So, the physical system we're talking about is a damped oscillator. What's that? Well, think about a mass on a spring that has some friction slowing it down. Or if you're an electrical engineer, think of an RLC circuit. Totally different fields, right? But here's the cool part. They're both described by the exact same second-order differential equation. It's all about that damping ratio, zeta, and the natural frequency, omega. Seriously, if you're going to burn one pattern into your memory, this is the one. Okay, and this is where it gets really cool. Once you've spotted that oscillator pattern, you can tell exactly how it's going to behave just by glancing at the numbers. If it's overdamped, the solution is just this slow, smooth return to zero, no wobbling. Think of one of those heavy hydraulic doors closing. If it's underdamped, well, that's your classic decaying sine wave. It's going to oscillate back and forth as it dies down, just like a plugged guitar string. And then there's critically damped, which is that perfect sweet spot, the absolute fastest way to get back to zero without overshooting at all. Just by seeing which case it is, you can immediately write down the right kind of solution. No guesswork needed. You see, this is so much more than just a neat little trick. When you really get these patterns down, it completely changes how you look at problems. It really is like having an engineering superpower. So why is this a big deal? Why does it matter so much? Well, think about it. When you're in a timed exam or you're on the job trying to model a real system, you just don't have time to rederive every little thing from scratch. Recognizing these standard forms saves you a ton of time. But honestly, it's more than that. It builds a powerful intuition. You start to just feel how physical systems are going to behave, and that is absolutely critical when you're designing something or trying to control it. So, at the end of the day, this whole thing is about shifting your perspective. It's about training your brain to stop seeing a bunch of symbols and start seeing the story behind the math. So, here's my challenge to you. The next time a differential equation lands on your desk, don't just jump into solving it. Take a second and ask yourself, what story is this equation trying to tell me?